So this week we're going to talk about atmospheric pressure, or how much the atmosphere weighs in different locations. And why in the heck do meteorologists care so much about this? We talk about low pressure systems and high pressure systems all the time in meteorology. If you tune in to a local TV station and hear their weather forecast, almost always they're going to talk about, well, there is a low pressure system moving somewhere, or there's a high pressure system approaching. Well, why are these important? What factors make these interesting to meteorologists? So with that, air weighs something. What is weight, or what is pressure? Its mass times an acceleration is a force. Well, guess what? Air exerts a force. There's all kinds of molecules moving about, and depending on how many of the molecules are in one spot and how they're moving about, there'll be more weight. Because the air is made up of various gases, the total air pressure is the actual pressure of each of these individual gases summed up. In other words, the pressure of nitrogen, the pressure of oxygen, the pressure of water vapor, the pressure of carbon dioxide, etc. All of these make up the air pressure. So, and since molecules do have a weight and they can have a kinetic energy, but we also have the force of gravity pulling all these molecules down. So with that, an average air pressure would be about 14.7 pounds per square inch. And that air pressure acts in all directions. There's air inside of us. So that's why we don't collapse under the weight of this air pressure. There's air in buildings. If you ever seen a pump that pulls air out of a tube or out of some object, as it's pulling it out, depending on what makes that object up, we'll say maybe it's flimsy plastic or whatever, as it's being pulled out, that object's going to crush because of the weight of air pressure that's pushing in on it. So you can really see an example of how heavy air is with those kinds of things. How do we measure air pressure? Well, one typical tool used to be the mercury barometer. We don't use that so much anymore because mercury's kind of hazardous. But typically, the air pressure, is around 29.92 millibars. That's the general average air pressure. Now, we like to use another unit. Why? Because it makes the math a lot easier. And we also deal mostly in metric units when we're doing the math equations in meteorology. So a millibar. 1,000 millibars is darn close to the average weight of the air. And that is directly relatable to kilopascals, which are a metric unit of weight. So, interestingly, air is compressible. You ever push water together? We know water doesn't compress, but air does. So why in the heck isn't all the air right down here on the earth? Well, it only compresses so far, but there is a lot more air down here in the low levels of the atmosphere than there is further up. If you go up a mountain, you have trouble breathing, right? When you get higher and higher up, well, that is because the air has been pushed down. It's compressed. So here is an example of pressure change with time. As you can see, pressure started out on the 13th at around 1,012 millibars. By the 19th into 20th, it was down to 1,019 millibars. And then by the time it's over, it's almost up to 1,020 millibars. So basically, we had a pressure change of about 12 millibars here. During that time, we had a low pressure system pass. Low pressure meaning just literally what it says, lower pressure, and then high pressure. That lower pressure was accompanied probably with some rain, some clouds, maybe even some wind. So, also, why does pressure change from one location to another? Well, let's start with air temperature. We said air is compressed. Well, that means it also can go closer together or further apart. So if I have an increase in kinetic energy, molecules are moving faster. They're going to tend to push each other further apart. Now, if I have exactly the same area, if I have very hot air, I have less molecules in that area than I do if I have very cold air. So the density varies depending on the temperature, and with that, weight changes. So if the air is less dense, it's going to weigh less. If the air has more density or colder, it's going to weigh more. So one significant influence on pressure is temperature. Also with this, if the air is all tightly packed together, if it's very cold, pressure is going to drop fast in the lower layers where all that air is compressed. Instead of being, oh, wow, it's all the same upwards, I get a drop in pressure exactly the same whether the air is cold or warm. No, if the air is cold, the pressure is going to drop a lot faster if I'm rising up in the vertical than if it's warm. Next thing, moisture plays a role. Oh, why the heck does moisture play that role? Well, moisture is, believe it or not, less dense than normal air. So, the more water I throw in the air, the less dense the air is, the less the air is going to weigh. So, on a very hot, humid day, the air is going to weigh less than on a nice, bright, cold, dry day. So interestingly, I've heard it in baseball and I've heard it in other sports. Oh, everything's going to go further today because it's humid. It's not going to go as far because it's humid. Well, guess what? Actually, the air is less dense. There's going to be less friction. So baseballs or other things will fly further in a very humid, hot air mass. Another interesting fact, air moves. So if it's coming together, we call it converging. And if it's moving apart, we call it diverging. Well, if the air is moving apart, well, air can't have a vacuum somewhere, right? So air is going to have to come from somewhere else to take its place. But when it's moving apart, the pressure is going to tend to be probably lower, or we're going to be pulling air down somewhere. Now, if that air pressure is moving apart, let's say divergence is occurring in the upper atmosphere, then you're going to wind up with air from below rising up. Well, that means the pressure at the bottom is going to be lower. You wind up with lower pressure. Exactly the opposite with a high pressure. The air is coming together aloft, pushing down, sinking. Air is getting pulled apart at the bottom, but that's going to be a high pressure. The ideal gas law, all it is saying is that if you know pressure or temperature or density, if you know 2 out of the 3, you can calculate the other one. All right. When air expands, it cools. You can feel that at a gas pump. At an air pump. When you release the air out of your pipe or out of a car tire, oh wow, that air is a lot cooler than when you're pushing it in. So, if I am lifting air up in the atmosphere, it's expanding, so that air is cooling. That is why in the troposphere, where we live, the air temperature cools with height. Now, coming down the same way, the air is getting compressed. The further down in the atmosphere it is, the warmer it's going to be. So, depending on air currents, they can change the temperature of the air. If the air is compressed, energy is being used, it expands. So that is a process that we can actually calculate. So we can say that air temperature as you're rising up, there's no moisture in this air whatsoever, it's dry air, will cool at the rate of 9.8 degrees Celsius per 1,000 meters. So if I told you you're going to climb a mountain today, and you're going to go up 2,000 meters, nothing in the atmosphere is going to change that day. Very little wind, nothing. You're going to wind up starting the day, we'll say, with a temperature of 10 degrees Celsius. 10 degrees Celsius is about 50 degrees Fahrenheit. Well, guess what? You're going to cool almost 20 degrees Celsius. You're going to cool 19.6 degrees Celsius. So your temperature went from above freezing to about 9.6 degrees below Celsius, negative, which is below freezing. It's going to get cold up there. So that is what's happening to the air as it's moving up and down. If it's coming down, it's warming at that rate. If it's going up, it's cooling at that rate. All right, we learned about latent heat, how it transmits heat throughout the atmosphere. Well, guess what? If a cloud forms, it releases heat. We said when condensation occurs, heat is released. So instead of cooling at the same rate at dry air, it's not cooling that fast. It only cools about 6 degrees per 1,000 meters. So that air parcel that is now wet is going to be warmer than the air parcels around it. Something we're going to need to keep in mind. So with that, I wanted to show you just a little bit here. So cold air. Let's just look at the surface map. We have a cold front. Why am I interested in pressure? We've already talked about that. Where there's low pressure, air is tending to rise. If it's rising, it's cooling. If it's cooling, it's getting cold. It'll wind up condensing and forming clouds. So we have low pressure off the New England coast. Guess what? There's going to be clouds there probably. We have big high pressure in the central part of the United States. Guess what? Not much in the way of clouds. We have high pressure over the eastern part, southeastern United States. Not much in the way of clouds. Notice, however, that even though temperatures are 30 degrees colder back here with this high than with this high, there's still high pressures. So high pressure is a relative term. It compares to the pressure around it. So not just heating something is going to make it low. You also need the air motion. Now, desert Southwest, low pressure out here. That is caused strictly by very hot conditions. Temperatures out there have been running well over 100 degrees. The air is very, very getting pulled apart. Low pressure is forming. Now, if I translate this, I said that the colder the air, the faster the pressure will drop in the vertical. Well, what does that translate to at 500 millibars? Halfway up the atmosphere. What happens is, where the air temperatures are colder, the pressure is going to drop faster. We actually have lower heights. Those lower heights literally correspond to low pressures in the upper atmosphere. So, where I had the colder Midwest, I now have a trough up aloft above it. However, I also have one here, and I have one off the east coast as well of the United States. They correspond just to the west of low pressure areas. And if you look at this big trough up here, go back to the surface, low pressure. One off the east coast as well. Even one to the east of this. So the colder air, yes, it's dropping the pressures, but there is a tilt. It's three-dimensional. You got to think in 3 dimensions with the pressures, just like all of the atmosphere. So I hope you got a little bit of why we care about air pressure. And this week, I want you to look at it. Hey, look and see if any low pressure has moved through your area. And the low pressure may be associated with a cold front, a warm front, maybe a high is just leaving. and pressure is going to drop. So think about that this week. And let me know if you have any questions.